Hello viewers, you are welcome back to my YouTube channel. In today's topic, we want to have a look at another important aspect in physics, and that is dimension of physical quantities. Again, dimension of physical quantities. Dimension has a special meaning in physics, and this explains how some quantities. Remember, in our previous class, we talked about the fundamental and the derived quantities. Any quantities that has the unit of length is dimensioned as, that is, our length is dimensioned using the letter L. While mass of a body is dimensioned using capital letter M. While the time is dimensioned using capital letter T. Again, any quantity that has the unit of length, it is dimensioned using letter L. Any quantity that has the unit of mass, it is dimensioned as capital letter M. So also, the time is dimensioned using capital letter T. Let's have a look at examples. For example, if you are asked to dimension area, the area is dimensioned, that is our length by breadth. Or length by length, as in the case of a square body, length by length. So it means area has two dimensions, that is the length and the breadth, or the length and length. So now length is L. Our breadth is also L. That is the distance, the breadth, both length and breadth. Look at this whiteboard. We have, this is, we have the length, and we have, of course, we have the breadth. So they are both talking about the distance. So here we now have L squared. So it means anywhere you see L squared, this talks about the area. Let's go to volume. Volume, 3 dimension, length by breadth and depth or height, depth slash height. So you can now see that here we are having 3 dimensions. This is L, L, and L, and this one will give us L cube. So it means the dimension of volume is L cube. Let's go to speed. Speed, of course, from our definition, that is the distance. The distance covered by a body in a given time. The distance traveled all over the time taken to travel such distance. Now, distance is dimensioned as L. Do not forget, our time is dimensioned as T. So I can now say the dimension of a speed is L raised to the power of L T raised to the power of 1. That is the unit of the speed. Of course, it's still the same as the unit of velocity, because velocity, we have our velocity, which is displacement. displacement all over time. Our displacement, of course, is also L all over time, that is T, which is L T raised to the power of minus 1. This is also the dimension for velocity. Let's go to acceleration. Acceleration, which is a what? Change in velocity. Change in velocity of a body with respect to the time. So, now do not forget, we have dimension our velocity. And what is it? That is L T raised to the power of minus 1 all over another time. That is, we have T. And this will now give us T, L T raised to the power of minus 2. That is the dimension for acceleration. Let's go to density. Density, of course, it is mass all over volume. What do you say is the unit of the dimension for mass? That is m. All over, what is the dimension for volume? That is L cube. I can now say the dimension for velocity, for density is m per m meter, that's length per meter cube. So we now have, this is the dimension for density. Let's go to pressure. Pressure. Pressure, of course, it is a force all over area. Force all over area. So we have force all over area. Of course, we have not dimensioned force. What is our force in the first place? Let us dimension force first before going to the pressure. Let's dimension force for better understanding. We have force. What is force? That is mass times acceleration. Mass times acceleration. Yes. We said force. Force is mass times acceleration. And what is the dimension for mass? Mass is capital letter M. And remember, we have dimensioned acceleration as what? That is L-T raised to the power of 2. So, anywhere you see M, L, T raised to the power of minus 2. That is the dimension for force. Now, from this, we can now proceed to pressure. Pressure. What is pressure? That is a force that is acting on a given area. That is a force all over area. Now, we have just dimensioned force. And what is our force? That's M, L, T raised to the power of minus 2 on area. And what is our area? L squared. And this now gives us M, L, T raised to the power of minus 2, L raised to the power of minus 2. And this will now give us M, L raised to the power of minus 1, T raised to the power of minus 2. That is the dimension for pressure. Let's go to moment. Moment of a force about a point. What's the definition for moment? That is force times distance. That is a perpendicular distance. Force times distance. Now we now have, what is our force? We have just dimensioned force. That is M, L, T raised to the power of minus 2. And what is our distance? Times L. Therefore, moment is M, L squared, T raised to the power of minus 2. So that is the dimension for moment. And lastly, momentum. Momentum. What is momentum? That is mass times velocity. Mass times velocity. What is our mass? Mass is m. What is our velocity? L t raised to the power of minus 1. So this is now the dimension for, this is the dimension for momentum. Do you understand? Yes. Yes. Here is another interesting question that is relating to the application of dimension. And the question reads thus: a small mass is suspended from a long thread so as to form a simple pendulum. The period t of the oscillation depends on the mass m, the length L of the thread, and the acceleration g of the free fall due to gravity. And here is the equation given to you. They said T is equal to K, M raised to the power of L, X, L raised to the power of Y, G raised to the power of Z, where X, Y, and Z are unknown. And K is equal to 2, therefore. Find the values of X, Y, and Z. Hence, derive an expression relating T, M, L, and G. Very simple. Let's see how this is being tackled. We have T is equal to K, M raised to the power of X, L raised to the power of Y, and G raised to the power of Z. Now, that is the equation given to us. Now, remember, in our previous class, we dimensioned the acceleration as what? That is, our G is dimensioned as L, T raised to the power of 2. So it means anywhere we see G, we substitute it for L t raised to the power of 2 in the above equation. So let us now see how we transform this. We have T is equal to K, M raised to the power of X, L raised to the power of Y. Now I want to substitute this G. Now our G now is going to be L t raised to the power of minus 2, open and close brackets, Z. We have T is equal to K, M raised to the power of X, L raised to the power of Y. Now let us now open this bracket. This one will give us L raised to the power of Z, T raised to the power of minus 2 multiplied by this Z. It will give you minus 2Z. Now, from this, let us now expand. If we expand this, we now have K, Mx, L raised to the power of Y, Z. Now I'm opening the bracket. Z raised to the power of L raised to the power of Z. Then we have, already we have 2 here. That is T raised to the power of minus 2 times Z. That is minus 2Z. Now, you can now see that we are having L raised to the power of Y, L raised to the power of Z. From the law of indices, we have T is equal to K, M raised to the power of X. I will now write only one L. We now have Y plus Z. T raised to the power of 2Z. Now, you can now see that the left-hand side of the equation and the right-hand side of the equation, I want to ensure that the two sides, they have the same parameters. The two sides, they have the same parameters. Now, To do that, we still go back to our indices. N3 raised to the power of, because here I'm having mass. And to this side, I do not have mass, but I want to introduce mass. I'm going by the rule of indices. N3 raised to the power of 0 is equal to 1. So I can now introduce, I will say, m raised to the power of 0. That is going to be m raised to the power of 0, that is 1. 1 times t still gives me that t. Now, l raised to the power of 0. And we now have t. That is the original t. Raised to the power of 1 is equal to k. M raised to the power of x, l, y plus z, t raised to the power of minus 2z. Now, let us now compare now. So it means m is raised to the power of 0. If we equate it to this m raised to the power of x, from the law of indices, when the bases are the same, the power must be equal. So, therefore, I can now say x is equal to 0. Beautiful. Out of what they asked us to find, we have found x. And what is the value of x here? X is equal to 0. Alright, let's go. Let's get that of L. L raised to the power of 0 is equal, when we compare it with this, we now have L, y plus z. So, when the bases are the same, the power must be equal. So, it now means 0 is equal to y plus z. Call this one equation 1. Now, it means y plus z is equal to 0. Let's equate the last one, which is our t. We want to equate our t. T raised to the power of 1 is equal to, when you compare it with the left-hand side, right-hand side, we now have t raised to the power of minus 2z. Since the bases are the same, the power must be equal. We now have 1 is equal to minus 2z. Therefore, z is equal to minus 1 all over 2. Call this one equation 2. Call this equation 2. So, it means we've been able to find our z, we've been able to find our x, it now remains our y. So, to find y, to find y, substitute z for minus 1 all over 2 in equation, which equation? We go to equation 1, in equation 1. And what does it say? Equation 1 says y plus z is equal to 0. But what is our z? Our z is minus 1 all over 2. I will now substitute. It means anywhere you see z, you put minus 1 over 2. We have y minus 1 all over 2 is equal to 0. Therefore, our y is equal to 1 all over 2. Yes, we have successfully found the values of x, y, and of course z. So that settles the first part of the question. Let's go to the second one. We want to we want to see the relationship now. Now, let's go back to original equation. What is our original equation? We have t is equal to k. M raised to the power of x, L raised to the power of y, and G raised to the power of z. Well, let us now replace those values. So we now have t is equal to k m. What is our x? Our x is equal to 0. So I'll put 0. L. What is the value of our L? Our L is what is our L? What is our y? Our y, we got the y to be equal to, where's my y? My y is equal to 1 all over 2. And what is my g? my G is minus 1 all over 2. Now, this one now means T is equal to K. Anything raised to the power of 0 is 1, so that one vanishes. We now have L raised to the power of half, G raised to the power of minus this, so half. So T, we now have K square root of L all over G. But K is equal to 2 double. Now we now substitute. Our T now is equal to 2 double. We have L all over G. So from this, one can conclude by saying, from this expression, from this equation, you can see that M does not appear. So that is telling us that the period, that is the period T, is independent on, is independent on the what? On the mass of a body. Now, from this, we can now see that the period is independent on the mass of a body, irrespective of the size of the mass, be it small or big. It does not have anything to do with the period of oscillation. So viewers, if you enjoyed this video, make sure you subscribe to this channel and like this video. Thanks for watching.